On hot gauge theories.
Thanks. So today I'd like to talk about one more application in the same general framework that I've been talking about all week, namely exploring aspects of the thermal dynamics of a hot non-abelian plasma, specifically a strongly coupled hot non-abelian plasma, which we're going to take to be n equals 4 super Yang mils. But today I want to change the setting just a little bit in that into my hot n equals 4 super Yang mils plasma, I want to think about what happens if you inject heavy quarks. This is, of course, motivated by the real world, where we have quarks of a variety of different masses, and experiments can even tag jets that appear to be the result of heavy flavor, so charm, anti-charm, bottom, anti-bottom, and so on. And so there's a lot of motivation for trying to understand the dynamics of heavy quarks that you imagine are pair produced at some time in a plasma. Now, once again, I'm not going to worry about any of the serious complications about modeling real heavy ion plasmas. So conceptually today, you should imagine that you have this box of hot plasma. And basically what I want to talk about is a version of the Gedanken experiment where you take some little projectile and you shoot it in. And my projectile is going to be a heavy quark. All right, to get off the ground, we have to say, what does it mean to add a heavy quark to our theory? So in particular, I want to add massive fundamental representation fermions, or they could be scalars. It really won't matter. To n equals 4 super Yang mils. You're all experts now on the statement that without messing around with n equals 4 super Yang mils, we have lots of reasons to believe it has an exact description in terms of in terms of string theory on asymptotically ADS cross S5. If I'm going to change the field theory, that's got to change the gravitational dual. And to do anything, we have to understand what it means in the gravitational dual to add heavy quarks. But you also have been hearing about branes all week. And there's a beautiful story that adding fundamental representation matter, well, I didn't go into the details. If I make it specifically what's called a hypermultiplet and do it in a way that preserves as much of the n equals 4 supersymmetry as possible, namely it'll preserve n equals 2 supersymmetry, then the result of adding a hypermultiplet is the same as adding a D7 brane to our dual gravitational description. The significance of that D7 brane, well, D branes are manifolds on which open strings can end. And in a very direct way, you should think of the endpoint of an open string stuck to a D brane as having something to do with describing a fundamental representation degree of freedom, because there really is essentially a color index, a Chan pattern factor associated with the end of that open string. OK, what does this D7 brane do? I'm not going to really try and derive this, but I just want to describe the picture. We have a D7 brane, which is an 8-dimensional manifold, because once upon a time, someone, Joe Polchinski, started counting wrong. Right? It has 7 spatial, a D7 brane has 7 spatial dimensions and 8 space-time dimensions. So what's it going to do? It's going to wrap 3 dimensions, namely it's going to wrap an S3 inside the S5. That leaves another 5 dimensions, which means it's simply going to fill ADS5, or more precisely, it's going to fill part of ADS5. It'll fill ADS5 down to a minimal radius. So let me just draw a picture and then. Oh, okay, before I draw a picture, what I just wrote would be a perfectly fine description if I wanted to do 0 temperature physics. I really want to do thermal physics. So, of course, now I turn the temperature on. And that means instead of being interested in dynamics in pure ADS5, we really now want to have a black brane at the center of ADS5. And so we really have a horizon down here. Okay, so in the same picture of sort of the radial direction of ADS space, adding a D7 brane is going to be filling all of ADS space. In other words, it's filling this part as I come down in radius, and it's filling all of the 4 transverse directions, which are just the Minkowski space directions. All right, but it's filling ADS space down to some minimal radius. Why is that? Well, I'm intentionally cooking things up, so I'm adding massive degrees of freedom to my field theory. So there's got to be some dial that corresponds to changing that mass. Changing the mass is exactly the same as changing how far down in ADS space this D brane comes. Now, in this way of drawing a picture, it somehow looks like this D brane has a sharp edge at the bottom, and that's a misleading aspect of this particular projection. In some other way of drawing a picture, it would be analogous to thinking about 2-dimensional space and just having some 1-dimensional manifold which doesn't intersect the origin. If I now make a plot of the values of the radius at which that surface exists, there'll be some minimal radius. Whoops, excuse me, I just said absolutely the wrong thing. If I just have a 1-dimensional line, it's a perfectly smooth 1-dimensional line. Obviously, there's a minimal radius at which it approaches the origin, but whatever point on this line is actually at that minimal radius, the line is just as smooth there as at any other point. So somehow thinking that there's a sharp edge to the D brane here is just an artifact of the projection. Okay. This story, which is due to Karch and Katz, I'm not going to try and derive any more formally, but I want to talk about its consequences. And qualitatively, they're simple. The point is, once again, that D branes are manifolds on which open strings can end. So start drawing some open strings. Here's an open string, both of whose ends points are stuck to the D7 brane. And claim, the argument is that you can and should think of such an open string as the dual description of some state in our new theory in which I have a heavy QQ bar meson. If I didn't have a black hole horizon, if I wanted to add an open string to this geometry, that open string has two endpoints, and I'd have to have both of their endpoints stuck to the D7 brane because there's no other place for that string to connect. Black hole horizon changes things. In addition to strings that look like this, I can have strings where one end just disappeared behind the horizon. All right, I hope it's already suggestive that the physical interpretation of this is a free quark. All right, it's a quark immersed in the hot n equals 4 supersymmetric plasma. That's a deconfining medium. That quark is free to wander around.
Somehow the open strings can end anywhere on the D7 brane, right? Not just on that special surface that you've drawn.
That is absolutely true. And so, I could have drawn this differently. Now, it is also true that the string dynamics in ADS space is such that, in essence, things want to fall down, which is why I've drawn all my pictures in this orientation. So, while there's lots and lots of string states where these endpoints are anywhere, if you now say, what are the lowest energy configurations, those are going to be configurations where the endpoint of the string comes down as far as it can.
There'll be some extra massive oscillations that the string oscillates in that direction.
Absolutely. Okay. Now, as I change the value of the mass of the heavy flavor that I'm adding, I'm going to move the minimal radius of that D7 brane. In the presence of a horizon, which is associated with some radial coordinate UH, there's a natural question. As you change the mass, and therefore change where the D7 brane ends, well, I can crank down the mass, which brings that position of the D brane in, and at some point it's possible that the D brane will actually fill all of ADS space down to the horizon. In essence, the part of the D brane can jump inside the horizon. So what I want to do today is talk about physics that you can understand basically by doing semi-classical string theory, where I don't have to work hard, I don't have to deal with fluctuations to get started. So I want to be able to look at, for example, open string states like this, and think of this as a semi-classical string. That means its length had better be large compared to the string length, because that's the length where quantum fluctuations in the string world sheet are dominant. So everything I say today is going to be limited by saying that I want the mass to be high enough so that the D7 brane ends outside the horizon. And I'm going to claim that that is equivalent to saying that the mass of my heavy quark is larger than some critical mass, and that critical mass is very close to a half square root lambda t. All right, so this is the same thing as D7. Okay, where does this come from? Well, D-branes are dynamical objects. When we add a D-brane to the gravitational description, really we should write down the action of that D-brane We should look at its equation of motion. In other words, we should look at basically the dynamics that controls how that d-brane wants to be embedded in the geometry. That's a calculation which one can and do. That gives you a precise value of the number there, and I'm just going to ask you to believe me that this is what comes out.
Sorry, if D7 is ending outside the horizon,
Pardon me?
If the D7 is ending outside the horizon, is UM not less than?
Thank you. Too many choices of U, sometimes where the boundary is at 0 and sometimes where the boundary is at infinity.
And the M equation is still correct then? M is still greater than M crit then? Or?
Yes, yes. So again, right, the boundary is UV physics.
Yeah.
So you shouldn't be surprised here. If I want an arbitrarily heavy quark, then the d-brane is ending very close to the boundary, and that makes sense because that's where UV physics takes place. As you decrease the mass of the quark, the d-brane is probing more of ADS space because you're getting more infrared dynamics. And I'll try and be consistent on my radial coordinate. Okay, so in this setup, there's lots of questions one can ask. Dynamics of a single quark moving through the system, dynamics of QQ bar mesons. Those could be mesons in which I have, say, angular momentum between the Q and the Q bar. They could be mesons in which I just have no angular momentum. I could add multiple flavors. I could have multiple flavors with different masses and have analogs of light-heavy mesons. Many of these things have now been examined. I'm going to focus on what's essentially the simplest class of interesting solutions you get out of this. So I'm going to focus on a free quark, or essentially an open string, which, as I drew over there, falls down in the ADS geometry and crosses the horizon. Right? You could pluck that string, and it could be vibrating in all kinds of different directions and have a complicated world sheet. Let's look for a relatively simple subclass of solutions where the entire world sheet of the string lies in a plane. What do I mean by that? Well, any string world sheet I'm going to describe by having two coordinates conventionally called sigma and tau on the world sheet. For the subclasses of solutions I'm going to talk about here, let's just identify our time variable in the background geometry T with the time-like coordinate on the string world sheet. I'm going to choose to put coordinates on the string world sheet. So the second coordinate sigma is really just the same as u. And then the statement is, think of this picture here as having singled out one of these spatial Minkowski directions. So to tell you, for example, the profile of that string right there, all I have to tell you is, as I increase u and come down in the geometry, how is the spatial coordinate x1 changing? And by saying I have a planar world sheet, basically what I'm saying is at all instances in time, the string lies precisely in the slice of the space-time that I'm drawing here, and it never extends in any of the other spatial Minkowski directions. All right, so that amounts to saying x1 will be some function that I'll just call x of sigma and tau, and x2 and x3 dash. All right, and again, this is just a simplifying assumption, but it will already give us some interesting results. So let me start with my ADS black hole metric once again, where I think these are the same coordinates I used back on Tuesday. Right? H of u is the function that vanishes at the horizon. UH is just a synonym for pi times t. Oops. Inverse. Hang on a second. Hang on a second. I lied. Sorry. It will turn out that the resulting equations will look a little bit cleaner and will match what I have worked out if I use inverted radial coordinates from what I talked about on Tuesday. I apologize. Which you see from the metric I wrote down here, in that spatial line element, I'm now multiplying by u squared instead of 1 over u squared. All right, so once again, we're changing things. And this is at least the third or fourth choice of radial coordinate you've seen. All right, but this is a coordinate which actually is a radial coordinate instead of an inverted radial coordinate. So that's actually rather natural. Good. OK. That's the space-time metric. Here's the relation between space-time coordinates and coordinates on the string world sheet. Take these, stuff it in, write out the induced metric on the string world sheet. All right, since t is tau and u is sigma, the first two terms really don't change. But now dx is really the derivative of my function x here times, well, is either a derivative with respect to sigma times d sigma, or a derivative with respect to tau times d tau. So I get a new term here. And I'm going to call it t. All right, and in the usual way, dots will denote derivatives with respect to time, and primes will denote derivatives with respect to ADS radius. Good. Expand that, clean it up a little bit. I have a du squared term. I have a dt squared term. And I have a cross term. All right, if you actually wanted to write out the induced metric as with components of a 2 by 2 metric tensor, then this would be g sigma sigma. This would be g tau tau, and this is g sigma tau. Question?
Is there any reason why you consider Minkowski time, or?
Yes, because I'm going to be interested in asking questions that involve Minkowski space physics. All right, things moving. So it's just because today I want to look at non-equilibrium properties. But as a result, it'll really matter. Good. So, if we want to do string dynamics, we start with the usual Nambu-Goto string action, which is nothing but a string tension times the area of the string world sheet. That area is simply an integral over whatever the physical ranges are of your coordinates on the string world sheet, d sigma t tau, times the square root of minus the determinant of the induced metric. Okay, so go up and look at those components of the induced metric and work out the determinant, which is this term times that term minus the square of this term. Clean it up a little bit. And this is what you get. And because we're working with Minkowski's signature, there's a relative minus sign. So if we had a static configuration where time derivatives vanished, then this is obvious. Then this term would vanish. I'd have 1 plus something which is manifestly positive. Right? And that's saying that I then have a non-degenerate metric on the world sheet. Right? But this minus sign is a clear signal that we're going to have to be a little more careful that if this term gets too big, this determinant of the induced metric can vanish, and that really means that you, well, it basically means you have a sick configuration. Okay, take this, take its square root. There it is in the action. Go ahead and vary the action to get some equations of motion. Clearly, I'm going to get, when I vary things, one term which will be x dot, well, the time derivative of x times the time derivative of the variation of x, and another term which is x prime times the u derivative of the variation of x. What's nice about this setup, I'm doing planar strings, is varying the string world sheet only means varying my one unknown function, u of sigma and tau. All right, so go ahead and do that variation, and then get rid of the terms which have derivatives acting on the variation by integrating by parts, as always. And the result is going to be what you get by varying this term, which will have an h, a u squared, an x prime. And because we had the square root of something in the action, we're going to end up with 1 over that square root in the denominator. And from integrating by parts, with respect to u, all of that will be differentiated. And from the other term, we'll have something very similar, h inverse u squared x dot over square root of minus g, time derivative of the whole thing. So we have a very simple equation of motion. Right? This term has to cancel that term. Good. All right, before I look for solutions of this equation, let me mention for future reference, let me go back to my little picture here. Anytime you have some string configuration, it has to make sense to focus your attention on some bit of that string world sheet and say, what is the density of energy? What is the density of momentum? Or what are the fluxes of energy and momentum associated with that little bit of the string? Said a little more formally, you have to be able to define currents, which are really now going to be two currents. They're describing fluxes on a two-dimensional world sheet. So we have to be able to find two-dimensional currents that describe the density or flux of space-time momentum. And in particular, the form momentum, which is Riemann-Minkowski form momentum, form momentum density on the world sheet, well, you can work out. I mean, it's basically an application of Noether's theorem. And in the interest of time, this is also something I'm just going to have to ask you to believe me on. If we had a completely general background geometry, a completely general string world sheet, the tau component of, well, which is really the density of component m of form momentum at some point on the string world sheet, is this expression where capital X's are just the functions describing the embedding of the string into the background geometry. Capital G here is just the metric of whatever background space the string is sitting in. The corresponding spatial component is almost the same. So for the specific case I'm discussing of an ADS black hole background geometry, you can plug that in. For the specific class of planar string world sheets, you can plug in my particular parameterization and really simplify these expressions. And if you were interested in the density or the flux of the x component of spatial momentum, that simply means you're interested in these two components. And again, a short exercise, just putting things together, which I'm not going to go through. Gives you this. And you can even verify that this makes sense. The density and the flux have to be related by a continuity equation. And so this had certainly better satisfy. And if you look at what I wrote here, and you look at that continuity equation, you'll immediately see that satisfying the continuity equation is exactly the same as the equation of motion I just wrote down. All right, but what this teaches us, well, several things. One thing is, if I want to ask what is the total momentum in the x direction associated with my string, well, I simply integrate over all of sigma of the x component of momentum density. All right, and similarly, if you wanted the total energy, you do the same thing with the time component, which I didn't carefully write down. Good. Now let's find solutions. Leave my picture there. Okay, there's of course lots of solutions to that partial differential equation, but let's just find some particularly simple and physically relevant ones. The simplest solution is, of course, to think about something which is static. It's not very interesting, but it's sort of a warm-up. There's certainly going to be a static solution where nothing is moving, and the simplest static solution is the only physical static solution is just going to be a straight string. What else can it be? Physically, it's describing a quark at rest. That should be the lowest energy state of a heavy quark that we add to the system. The string is going to be sitting in its lowest energy state. And if it's both static and straight, that's just telling you that both x dot and x prime vanish, and that trivially satisfies the equation of motion. The one thing that you get out of this, which is not quite so trivial, is to ask, what is the energy of this configuration? Well, I just told you what that energy is. We have to be able to write it as an integral of the radial coordinate, which I'm going back and forth between calling u and sigma because they're just synonyms for each other now. This string is running from, well, if I want to make the energy as small as I can, I want the length of the string to be as small as it can. The smallest it can be is if it has its endpoint at the minimal value of the d brane, which is what I called u sub m, and then it runs down to the horizon at u sub h. All right, remember that u sub h, from right up there, is proportional to the temperature. So what this is teaching you is the temperature-dependent change in the energy of a static quark. This is really equivalent to my discussion back in my first lecture of the free energy associated with inserting a single static quark into the plasma. All right, so if we were at 0 temperature, this energy would just be T0 L squared um, and this, by definition, would be the mass of the heavy quark. If I'm at non-zero temperature, you look at this and you have an energy which is that mass plus some correction, which is just the same as what I called the free energy shift in my first lecture. And you look at this result, and it tells you that that correction goes like T0 L squared UH, and you're tempted to stop there. It's actually a little complication. As you turn up the temperature, you're changing, obviously, the space-time geometry. As you change the space-time geometry, you actually change the embedding of that d brane, because that d brane responds to the geometry. So what I mean by the minimal position of the d brane isn't really something that's fixed once and for all by telling you the mass, because when I turn on a temperature, the embedding gets to adjust a little bit. If the quark is heavy, this correction goes away. So if you want to think about the leading behavior for arbitrarily heavy quarks, I could just stop with what I already said. But in general, there is a second term here. Okay, this term, which for sufficiently heavy quarks is the only one that dominates, T0 times L squared is square root lambda over 2 pi. UH is pi t. So what we're seeing here is that that the size of the thermal corrections to the energy of a quark inserted in the plasma scale like square root of lambda times the temperature. And moreover, it's negative. Right? Its interaction with the rest of the plasma is actually decreasing the energy of this quark you've inserted. That's actually reasonable. You have attractive interactions. Well, it's the same behavior you get in weak coupling if you thought about a heavy quark, and there you can certainly think about it just as, you stick a charge into a plasma, there are attractive interactions which is going to cause it to attract opposite charges around it, and that'll actually decrease the energy. Okay, that's the static solution. It's not that interesting. Let's look at dynamic solutions. All right, once again. Finding a solution that's describing a moving string is the same thing as describing a moving quark. But remember that we're describing dynamics of something moving through a plasma, and this is a dissipative medium. Right? We're really doing condensed matter physics. So if I literally just injected some high energy projectile into this plasma and watch it, you know what has to happen. It's got to slow down. It's got to transfer energy to the medium because in essence there's friction. That's what you mean by saying you have a dissipative medium. So there has to be one class of solutions which describe exactly that. A time-dependent excitation moving through the plasma but slowing down. All right, there are such solutions. They're not the easiest ones to find. A different class of solutions, which will be a little bit easier, is to look for solutions where the projectile doesn't slow down. But I just told you that's not possible. Well, it's not possible if you have a projectile that's moving through a dissipative medium and it has no other forces acting on it. Okay, so if you want to drag that projectile through the medium at a constant velocity, that just means that some external agency is going to have to be exerting a force on that projectile, and the magnitude of the force, if I want its velocity to be fixed, the force with which I drag it must exactly balance the friction force, or the drag force, exerted by the plasma. All right, so looking for such solutions is actually a perfectly nice way of exploring the dynamics of the drag or the friction of the plasma, because it just converts that problem into understanding how large an external force you have to turn on in order to produce a constant velocity solution. Okay. Before we do it, let me also note, this is really a perfectly reasonable thing to do physically as well. We've added heavy quarks to the theory. Adding heavy quarks means we've actually enlarged the symmetry group of the theory, and there's a flavor symmetry. If we have one flavor, then I'll have a U1 quark number symmetry. If I have multiple flavors, I'll have a larger group. You're perfectly free to imagine gauging that group in just the way that I talked about on Wednesday, and imagine having some electric field that couples to flavor but doesn't couple to any of the bulk degrees of freedom of the n=4 plasma. And that makes perfect sense in this description. In fact, there are flavor gauge fields that live on this D-brane. So if you want to say, what is this external force that I'm using to drag the torque, the simplest answer is just turn on an electric field. And it'll do exactly what you want. It'll pull quarks of one charge in one direction. It'll pull quarks of the opposite charge in the other direction. For any given value of the electric field, it'll accelerate a quark until the force of the electric field exactly balances the drag force of the plasma. So there'll be a relation between the velocity and the magnitude of the external force.
But computing the drag force is not the same as computing the energy loss of the quark transversing the plasma, is it? Because I mean, the energy loss could be dependent on the velocity which the particle has, and so.
Let me just say we'll come to that in just a little bit, and we'll be able to have formulas that express that. Okay, to actually do this, for a stationary solution, I want it to have constant velocity. That means I want my string to have some profile that whatever it is just rigidly translates in time. So that's the same thing as saying my string is going to have some profile at time 0, and then I'll just have a term velocity times time, which is describing that rigid translation. All right, therefore, although I'll now have a time derivative because I have a velocity, that time derivative is constant. A spatial derivative only differentiates this term and knows nothing about the velocity. My formula for the induced metric only depended on x prime and x dot. And therefore, all these things are now independent of time, even though I'm describing a moving solution. That's just because it's stationary. So the time derivative term in the equation of motion immediately drops out. The equation of motion reduces to a single ordinary differential equation where the determinant of the induced metric, given by what I have on the upper board, I can now specialize just because x dot is constant. And so this is now L squared times 1 minus h inverse u squared v squared plus h u squared x prime squared. And I wanted this square root. Good. Simple. Derivative of something equals 0. So this stuff is a constant. That gives us a one-dimensional ordinary differential equation. This stuff inside equals a constant. There's an x prime here. There's also an x prime hidden down in the square root of the induced metric. Nevertheless, take that condition, solve for x prime, turn it into some completely, well, I mean, you've solved it by quadratures.
Are you using Dirichlet boundary conditions at the horizon? Keep the one end of the string there?
Let me write down the relevant solution of this equation first, and then you can ask your question again. Okay. So there's some constant c, square root of minus g over hu squared. Something has to determine the value of that constant. That something better come out of the physics of the situation. Whoops, I really didn't mean to write that down. That's some intermediate expression. Let me just clean it up. So that's what we get from a first integral. Take that first integral, plug it into this expression for square root of minus g, clean it up a little bit, and we get some expression for the determinant of the induced metric that now involves the velocity, and it involves this integration constant c, whatever it is. But what's significant is I have a ratio here. As u varies from the horizon out to infinity, as long as the velocity is non-zero, there's going to be some value of u where this numerator vanishes. That's going to be a 0 of the induced metric, which really means I have an unphysical, degenerate string world sheet, which is garbage. I don't want that. The only way I can avoid that is to say, but I have a ratio here. The denominator also has a 0. That's actually even worse. That's going to make a pole and make the induced metric blow up, unless, of course, I arrange for the 0 of the numerator to exactly coincide with the 0 of the denominator, and then life is good. All right, that has to be the case. That's the only solution that's physical if we're going to describe a solution in which the string does something, but it looks like my picture, where it moves from a d-brane whose edge can be arbitrarily close to the boundary all the way down to the horizon. Okay, well, as I just said, that determines the integration constant c up to a sign, because it's only c squared over there. And at this point, finish it off. Once c is determined, take this, go solve for x prime, integrate it, and in fact, you can do it analytically. So the result is going to have a second constant of integration, which will be nothing other than just the position in x of the string at time 0. So we'll have terms which are just x naught plus vt plus or minus something I can write as velocity times some profile function that I'm calling f of u. And that is nothing but an arctan and an inverse cotangent, which you can rewrite in terms of logs if you prefer. Okay, now let's talk about what this looks like.
You seem to make a simplified assumption that velocity is homogeneous.
The velocity is a number.
Yeah, but it could depend on you in principle.
Not if I'm looking for a stationary solution. So I really want a solution which time translation has a trivial action.
That means the velocity on the horizon is the same everywhere.
Yes. Right. So you can, of course, look for more general solutions, but they won't be these ones which describe a constant velocity excitation.
So you did tell us what the sort of U min was for the case with the electric field turned on in the brain, right? That also changes.
That also does, but in the limit where the quark is heavy, changes in the embedding of the D brane become negligible. So let me just not worry about it by saying, let's think about truly heavy quarks. It's a non-trivial issue if you want to bring the quark mass down to the lower limit where this whole description makes sense.
Why didn't the electric field on the brain enter into the equation of motion that you're solving?
Good question. So what did we do here? We solved the equation of motion, and you haven't yet heard me say a thing about boundary conditions. In our other application, that's been a big factor. Boundary conditions at the horizon, boundary conditions out of the boundary. So in particular, I have some profile for the string here. And what does that profile actually look like? As u approaches the horizon, this ratio approaches 1. If you say, what is the inverse cotangent of some number which is very, very close to 1, the result is enormous. So this function is going to diverge as u approaches UH, and actually in a negative direction. On the other side, if I make the mass of the quark arbitrarily heavy so that I'm interested in evaluating this function for values of u that are arbitrarily close to the boundary, which means very large values of u, then, well, look at both of those terms, and they both go to constants. And in fact, this has been cooked up. And f prime of u goes to 0 as u goes to infinity. But what also doesn't figure into my solution here is the actual mass of the quark, or equivalently the value, the maximal value of u where I'm actually going to be interested in this solution. Right? Suppose I have some large but finite mass quark. I have a solution here for some string that's going to come down and do something. It's not satisfying Neumann boundary conditions at that endpoint. Normal, strings in Minkowski space, you always end up with Neumann boundary conditions at the endpoint. This solution fails to satisfy Neumann boundary conditions. That doesn't mean it's non-physical. That failure to satisfy Neumann's boundary condition is precisely a reflection that there's a force acting on that endpoint. And the actual slope with which that string comes in to its endpoint, you can directly translate into that force. So instead of starting with the electric field and finding a solution, in essence, what's easiest to do here is to go backwards. We found a solution. Now, depending on the mass of the quark, we could evaluate the slope of this configuration, and that would give us the electric field that's required to produce this stationary solution. I hope that's clear. Okay, so one thing I do have to talk about is we have two solutions. There is a plus or minus ambiguity.
Excuse me. Can I ask about t dependence on c? Because there appears to be a t in the denominator of the c equals plus or minus UH squared term. Can you see the second line on the board you're looking at? Yes, that a t? square root
I'm
t.
sorry, no, that's sloppy handwriting. That was just a square root of 1 minus v squared. Thank you. Right, those square roots, those denominators of square root 1 minus v squared that are reminiscent of special relativity, which is a bit of a surprise because we have a background plasma. You don't expect anything here to have normal relativistic form. Okay, so we actually have, because of that plus or minus sign, two different solutions. One of them, if you plot it and you say everything is moving to the right with velocity v, looks like this. The other one just looks like the mirror image, except again, everything is moving to the right. What's going on? Well, I gave you formulas for flow of energy and momentum along the string. You can take this solution, you can plug it back into those formulas and say, what is energy and momentum along the string doing? In this solution, there is a flux of energy down the string in the direction I just drew. In this solution, there's a flux of energy in the opposite direction because these two solutions are, in fact, just time reversals of each other. That had to happen, of course. We have time reversal invariant equations of motion, even though we're describing a physical application that involves dissipative dynamics. Okay. What do? We look at this. We say, this makes sense. There is a flow of energy from the UV end of the string, where it makes sense to think of the energy of the string as energy associated with the quark, down the string toward the horizon. Once again, physics close to the horizon you should think of as IR physics. So you should think of energy flowing down here as energy that in a dual four-dimensional description is no longer highly localized with the quark. That makes sense. That's the quark transferring energy to the medium. This makes little sense. This is the plasma transferring energy to the quark, right? This is energy flowing out of the black hole horizon. So we do the simplest thing. Cross it out.
But shouldn't, once you include the electric field, you actually break this time reversal in there because it's coupled to velocity, just power velocity. So it should be, if you really start with this kind of setting where you took a boundary condition.
I mean, the equations are still, there's still a time reversal symmetry when I really add the flavor electromagnetism. I don't think that that can just drop out of the equations. I think this really has to be physical input. Okay. So we're almost done, at least with this part. And let's just finish it up. So let's take the solution, which does appear to have a sensible interpretation. Go ahead and now just do what I said quantitatively. Calculate the rate at which energy or momentum is flowing down the string. And I don't think I have the time to just go through the trivial intermediate step, but it really is straightforward. That's a square root of lambda. And you get beautifully simple results for the rate at which energy or momentum are flowing down the string, which once again you should interpret as the rate at which the quark is losing energy and momentum to the plasma, which for this stationary solution is, of course, the same up to the sign as the rate at which the external field, the external force, is feeding energy and momentum into the quark in order to hold its velocity constant. All right, first thing you see is the answer scales like square root of lambda t squared. You've seen a number of physical quantities, transport coefficients, photo emission spectrum, Debye screening lengths, which simply turned out to have finite limits as lambda goes to infinity. This is different. It's different because really this reflects string dynamics, and that square root of lambda came straight from the tension, which was the prefactor of the Nambu-Goto action. So you couldn't avoid it. But in terms of applications, that's a big deal. So if you say, how big is this? It's going to depend on picking an actual value for lambda and plugging it in. And then there's velocity dependence, and it's remarkably simple velocity dependence. In fact, if we have a very heavy quark, in general, if you have a particle propagating in some medium, it's really a quasi-particle. The relation between its momentum and its velocity has no reason to be the same as a stable particle at zero temperature. There are thermal or there are medium corrections. But if this is a very, very heavy quark, if we were at zero temperature, we'd have the usual relativistic relation between momentum and velocity. And if it's sufficiently heavy quark, this must be a good approximation too, because all I'm saying is this term is huge, and the size of the thermal corrections we already saw scale like square root of lambda t. Okay, if you look at that and you look at this, you see a very simple result. The rate at which this quark is losing momentum is simply proportional to its momentum with some friction coefficient I'm calling mu, which is explicitly pi over 2 square root of lambda t squared over the mass of the quark. All right, that's a beautiful result. It's a bit of a surprise. Think about any more normal medium where we do laboratory experiments and we have a little better intuition. Think about normal matter. Shoot a relativistic electron through normal matter. It'll lose momentum, certainly. Increase the momentum of the electron. Shoot it through. It'll lose momentum. But notice what this says. This says the rate of momentum loss is strictly proportional momentum, no matter how large the momentum is. So in fact, well, 1 over mu it would be the time to lose a fraction 1 over e of the momentum, right? Or up to a factor of velocity. Right? This is a length over which our excitation is losing a fixed fraction of its momentum. That's really peculiar. That says you double the energy, you double the momentum of the projectile, and suddenly it loses momentum twice as fast, so it has exactly the same length to go in order to dissipate a fixed fraction of its momentum. Typically, in systems we're more familiar with, as you crank up the momentum of the projectile, at some point it sort of blasts through the medium, barely even seeing it. Right? So you typically expect the length scale over which you lose an order 1 fraction of momentum to get longer and longer as the momentum goes up. So this is very strange. Now, it's worth bearing in mind the assumptions that have gone into this, right? We've done this whole calculation in this leading semi-classical string dynamics, which once again means we've really, well, I don't want to write lambda goes to infinity because our result depends on lambda, but this whole analysis is valid for large values of lambda. But the velocity never entered in any of that. So this whole analysis, I mean, either ADS CFT duality is fundamentally wrong, which I have no reason to believe, or this answer is the correct answer for the energy loss for any value of the velocity less than 1 for sufficiently large lambda. However, it is quite possible that the value of lambda that's sufficiently large for this to be a good approximation can get larger and larger as the velocity approaches 1. In other words, it's quite possible that there's some non-uniformity between sending the velocity to 1 and sending lambda to infinity, if you will. Trying to say the same thing a little less formally, it's quite possible that if we really understood corrections to this better, we'd be able to say that this formula is valid for velocities less than something which would scale like lambda to some power. Right? All I've shown you today is that if you fix the velocity and send lambda arbitrarily large, well, I've argued that this should be a good approximation. Right? It's quite possible that this remarkably simple, surprising form is valid for velocities. Oops, I didn't mean what I wrote there at all. I meant gamma. Right, the gamma factor, which can be arbitrarily large. It's quite possible that if this gamma factor scales as lambda to some power, some positive power, then you enter a different regime in which physics is more complicated. And that is something which is not well understood today. Okay, I'm supposed to be quitting, right? So I'll just stop here mentioning that there's lots of interesting follow-up work, including looking at fluctuations in momentum. This is really telling you about the mean loss of momentum. I was also going to show you some wonderful pictures of the wake of the quark, which is an effort to say, where does the energy or momentum that's being lost by the quark, where does it go? It's being transferred to the medium. But where? We should be able to make a picture of it. And that's actually now been done, and I have some beautiful pictures of it, but I'm out of time.
In 3 minutes.
You're the boss.
He's nodding.
Can you answer a short question?
Sure.
What is the expression for the drag force of weak coupling?
Good question. At weak coupling, it has been calculated, and I have to now try and drag this out of my memory. It goes, well, first of all, it has a complicated velocity dependence. It doesn't satisfy the same very, very simple velocity dependence. So at weak coupling, it scales like lambda squared, because it's basically collisional energy loss with cross sections which go like lambda squared. So the force you can write as lambda squared times t squared times some non-trivial function of velocity, where you just have to look at plots. And I should just refer you to the paper of Guy Moore and Derek Teeney, who did that calculation in hot QCD, or Alexei Vuorinen and my student Paul Chesler, who did the corresponding calculation in n=4 super Yang mills in order to see how they compare. Okay, so I won't tell you what it takes to go from this solution for this moving string to a calculation of expectation value of energy momentum tensor, although it's just an application of stuff you've already heard about this week. And if anybody wants to ask me about it privately, that's certainly fine. Let me just flip through some pictures. This is x parallel. I have a quark moving up and to the right. And in this first picture, it's moving at 1/4 of the speed of light. And what's significant is that in any conformal field theory, you know that the stress tensor is traceless, and that turns into a statement that you know exactly what the speed of sound is. It's 1/√3. What's relevant is that 1/√3 is larger than 0.25. So this is a projectile moving through a medium subsonically. All right, and what do you see? You see an excess of energy. It's sitting right here. It's moving this way. You see an excess in front of it. You see a deficit of energy density behind it. And I suggest you should think of that just the way you think of some boat moving through water. It's pushing on the water. It's piling up in front of it. There's a little deficit behind it. And this whole sort of perturbation in the energy density just moving right along with the quark. It's not that exciting. This is a lot more fun. This is a supersonic quark moving at 3/4 of the speed of light. Again, up and to the right. And here you have a nice picture of what you could call Mach cones. If you have a supersonic projectile, it can make a shock wave. In approximations that are commonly used for supersonic bullets in air, you completely neglect the viscosity of air. You completely mangle your description of physics on length scales of the mean free path, and in that approximation, a shock wave looks like a discontinuity. As soon as you treat the physics right, that's never true. Physics on the scale of mean free paths will give you viscosity, which changes things and smooths out discontinuity. So these sort of more gentle excess of energy density is coming out at exactly the same angle that you calculate from the classic freshman physics interference discussion that determines the angle at which you have Cherenkov radiation, or in this case, the angle at which you have Mach cones coming out in a fluid. All right? And the nice thing here is that you really have a unified description that's correctly treating the physics on scales that in fact are small compared to the de Broglie wavelength of a quark. Quantum mechanics is important, out to large distance where hydrodynamics is important. Right? Virtually all other applications, you never do that. You completely mangle the physics in one regime or the other. Here you just do it. Here's a picture that's exactly at the speed of sound. In this case, that Mach cone isn't a cone, it's a flat plane that just moves parallel to the quark. And that's what you're seeing here. And just hot off the press, I have some pictures of now not energy density, but energy flux, or equivalently momentum density. And I'll just flip through 3 pictures for the same 3 situations of momentum density. This is the subsonic case. And, well, there's excess of momentum density behind it. I don't know if you can see the arrows very well, but this is actually momentum flux moving in the direction of the quark. That's saying, well, it's just like a boat again. You have a boat running through water, and behind it, there's some water that's moving in the same direction as the boat. All right, nice, smooth. Here's the supersonic case. What's interesting here is you really see a separation. There's stuff going on this Mach cone. And then what you see here is there is also essentially a wake behind it. And that's really diffusive physics. This is really the separation of the dynamics of momentum density into longitudinal components which are associated with sound waves and transverse components that are associated with diffusion. All right, I don't have any more time to say about it. Here's just the corresponding one exactly at the speed of sound. And with that, thanks.
Okay, since coffee's getting cold outside, I suggest we leave questions till the break, and you can ask Larry privately. But I would just like us all to thank Larry again for a completely beautiful session.